Hi, I'm Andy.
I'm Alex.
And we're co-founders of Kortical, and we like talking about AI and machine learning. Today we're going to talk about what good data looks like and give you top 5 takeaways. Okay, so just as a little bit of a setup, if we're to think about the equation for how good you end up doing with a machine learning project, you might think something like quality of the data, how good the data scientist is, and how many iterations you do multiplied together. And the reason why it's just sort of like important to say like the multiplicative factor is just because like if you don't have good data, it doesn't matter how good your data scientist is, it doesn't matter how long you spend working on it, you're never going to get back to a good solution, right?
Right.
So that's why we think sort of just talking about the top 5 takeaways, and what we're going to do is we have each independently got our list together, so we don't know if we're completely harmonious. We might have thought about the same top 5 takeaways, so there might just be 5 takeaways. If we've got a whole different take on the whole thing, which is more likely, then there might be 10 takeaways. Okay, cool. So we're going to do it one each, and then we'll see how we go.
Reverse order as well.
Reverse order.
Build to a crescendo.
Mine have no order. Anyway.
Right.
Go. Point 1. What's your top 5 takeaway?
Okay, so like it's important to just have kind of a good data provenance. So knowing you don't have any gaps in your data, essentially, knowing that it was all kind of recorded as part of like the same process or system, or at least the kind of physical things that are happening that you're recording, or the digital process that you're carrying out has sort of remained consistent, because that could be like a massive gotcha if you're not careful. They've changed from one system to another at some point in time, and they've tried to keep the data model the same, but for example it's using a different way of like representing dates, or it's representing quantities differently, or it can be something that's fairly hard to spot. It can be catastrophic for, especially if you are trying to do something over time, and you train your model on system A and then your test set is actually from system B, and you're going to have all sorts of interesting problems that you will find it very hard to catch because the data looks great. So it's kind of why the input to do kind of data-driven analysis on your data set, especially if there's like a time component.
No, that sounds good. I mean, I agree with you for the most part, but can you think of cases where, is that always true, or is it actually sometimes it's okay?
Yeah, I mean, it's broadly, it's the most important where there's a kind of time element. Not all data sets really have that. For example, if you're just talking about some snapshot thing like a credit scoring thing where you've got all just aggregates that are kind of pre-generated, that might not be so important. Or like, something like shopping basket analysis or something what you previously bought, that's not necessarily a time component to that. Could be, but it doesn't have to be. And the models work great if you don't.
Okay, but imagine I've got like a whole bunch of shopping data on my customers, and I previously was using one CDP that had one type of format, and now I've got a new CDP that's got a new format. Should I throw away all my old data because it's in a different format to the new data, or should I try to combine both of those data sets but just be aware of the fact that they're different?
Yeah, I mean, it hopefully fairly obvious. I mean, if you're just looking at the products, so it should just be like a product ID. So, it should be like when you do that migration, there should just be a mapping that occurs. It's probably harder to have subtle issues, although that's almost certainly cases where you can find that's true. So probably, all data is time series data to some extent. It's just not all machine learning problems need to be represented as time dependent. You could just use a random sample to do your train test split, for example, rather than a time, sort of a point in time to say your training test set, and therefore some problems are going to be more robust to these kind of issues inherently just because they're not so sort of based over a time spread.
Yeah, that makes sense.
All right, well, how about you? What's your, no particular order, first takeaway?
I think the first thing that I'd like to talk about is the rule of thumb target variable stats. So basically, one of the things that we're always asked about with data is basically, is my data, good enough? And I think one of the first things that we really have to always check on is the target. And it's basically sort of saying, right, well, we kind of have some good rules of thumb, right? So if it's a binary classification or a regression, we say, hey, if you've got 1,000 examples, you'll probably get a pretty good model. Like, it might make some errors, but they probably won't be like embarrassing errors or like unexplainable errors where a customer would be like, why the hell did it say that? You know? And then I think also sort of like for multi-class and multi-label, we often, because it tends to be sort of more classes and more labels, we often sort of like lower that down quite a bit, and then, you know, we have to say sort of like, well, like if there's 50 examples, it's probably going to be all right, or if there's, you know, at a squeeze maybe 20 examples, it would be all right.
Yeah.
But, you know, but I mean, typically with those, you're looking at sort of like, there's going to be a couple of classes that have tons of examples that you're able to predict really well, and it's really about trying to find the boundary of which ones should you just sort of group together into an other or predict differently or do something like that. But I think the thing is like I say, like these are rules of thumb, and then there's always the exception. So the thing is like why we kind of like wincing around this topic a lot is because, you know, I mean there was that example from the bank where we got in there and it was doing, you know, can you build an NLP thing off 60 emails, you know, because that's all they could get through because of their data security process was so, you know, constrained. And so we had these 60 emails that were created, that were, you know, and you build a model off it, and it's like, it's actually okay. Like, it's actually viable. It was good enough to be that first base model that you could then have more data come in off, do the retraining, get smarter over time, and do that sort of thing. So I think the thing is like, obviously, like, we created the Dataprep tool, so you can kind of like get a, you know, an analysis of this sort of stuff in like a couple of minutes, but obviously usually you have to consider these things in the abstract before you even kind of get to the point you've got your hands on the data, and sort of that's when we use these rules of thumb to try to get an idea of that, you know?
Yeah, and just before someone like writes in the comments, oh, you can't possibly build a classifier on 60 emails. You absolutely can if the content of the email is quite different, and so what we were trying to do there was like decide what business unit an email should go to. So there's quite a long email and quite a few keywords that are different, and actually that makes it quite viable. I certainly wouldn't want to be trying to like, build like a sentiment analysis or something more arcane off of 60 emails.
Oh, absolutely. And I think the thing is like the real thing is basically it's like it really is about that complexity of what you're trying to do with the data. So it's like you might have something where, you know, you're trying to do something with, you know, even with a binary case, and actually there's a pretty strong basic signal. And if there's a really strong basic signal, well, maybe even with a small few examples, you'll be able to pick up something which is pretty good to start with, and then the more subtle signals can kind of come in later. So it's really about signal strength for the class in the data, and you know, the less strong that is, the more examples you need, or the more sort of subtle the boundaries are, the more data examples you need to be able to create those sort of more complex surfaces, essentially.
Yeah, and you touched on something that I hadn't thought of, but it's a really good point as well. It's like, you've got a target, but what is the target actually? What do you mean by churn? Like, does that mean they haven't used the site in a week, a month, or 3 months, or they've actually said, please stop emailing me, I'm never going to use you again, or they gave you a negative review on Trustpilot? Like, it could mean any of those things, right? So I think sometimes as a data scientist, you get a data set and you don't kind of question some of the underlying business decisions that have been made to create the target, and often that's incredibly critical to understand, to help you understand what's going on with your results and help you sort of do the subsequent kind of business case stuff.
I want to discuss this a bit more. I feel it kind of leaks into one of my other points. So why don't we just do, what's your next point?
Similar to that, actually, kind of understanding your data, so really knowing what the features mean, what are they representing. For example, you can often get a case where you've got a massive data store that's been inherited, so the stakeholder's like, yeah, I know what these ones mean, I think I know what that one means, and he's on holiday, but he's the only one that knows what that one means, and forget about the rest of these. And you know, SAP is great for that, for like, literally having millions of columns which have arcane German acronyms as the names, and someone at some point knew what it did, and now basically no one does. But we find that this one's useful for predicting something, but we don't know why. That's not ideal, really, because you know, you always really want to know that link between the representation of the business, i.e. the data, and you know, what's actually happening under the surface. And if you're just going blindly off of sort of some variable that just seems to be good, it's really hard to tell whether that's like a leaking variable or something that we really shouldn't be including. And also, you know, how do we know if we're going to have that reliably at predict time? And it sort of comes with all sorts of potential problems like down the line. Another thing that actually is quite important is, especially for trust, trying to get your head around what's going on, is like looking at the data yourself and trying to understand if you could make a prediction from it. Like I remember doing something in utilities trying to predict leaks, and you're just looking at data and it's like, oh, how many lengths of lead pipe and how many meters of this kind of pipe, and you know, you can just look at it and see, yeah, I can sort of see what we might need to do as a feature engineering step here, because actually it's to do with, you know, the total amount of this kind of thing and this kind of material, and it's a massive advantage in terms of the kind of the value add as a data scientist to be able to build features that help your machine get to, like, you know, get to the right answer easier than having to blindly try and cross-correlate features at random. And you know, obviously as soon as you get to like third order things, that space is just almost, you know, unfeasibly large. So if you don't know what your features are, or you have a very limited understanding, very hard for you to do effective feature engineering, which is kind of sometimes the most important thing you can do to kind of get your problem to that sort of, you know, really high level of accuracy.
I think that ties really well into one of my points, which is that representation matters. Basically, like how you represent the data to the machine learning algorithm is almost equally as important as the algorithm and hyperparameters that you pick for that algorithm. So I think the thing is that sort of, you know, we've often seen that people spend a lot of time trying to coax the machine learning parts, or they you know, trying out these different feature engineering techniques, but they don't spend time to really understand or think about that data and how they can change the data to make the project better. And I mean, for us, given the platform, basically that sort of model selection and hyperparameter tuning, I mean, it's essentially a solved problem. So we spend almost all of our time in the how do we represent this differently, and you know, this sort of stuff. And you know, we have projects that go from, you know, non-viable to hugely awesome, and that's really all about how we're representing that data. You know, I think there's a great example from when we went into a competition and we were head to head against a company that we're not going to name because we don't, you know, we're nice like that.
Classy.
And they basically got up on stage and they went, you know, garbage in, garbage out, talking about the data and saying, look, you know, we had to look at this, but it was completely not predictable. And then this is around sort of trying to predict, you know, what someone's going to buy next from a stock perspective. And the thing is that if you're just trying to do this from pure stock movements and trying to just feed that trail of stocks into your algorithm and saying, hey, what's someone going to buy next? That's an incredibly challenging thing. But if you're actually speaking to the domain experts, you're trying to dive in and understand the data, and they say, hey, actually, like, we can build up a portfolio representation if we just look at everything they ever traded. And then we can look at like what's in their portfolio, what do they just have in their portfolio, and build up like these sort of portfolio view of the data rather than this pure stock ticker feed. Then we represent that to the machine learning algorithm, and suddenly, bam, like it's actually really predictable, and we can get a really good model out of it. And that's just for saying, well, you know, it's all coming from the same data, but how you present it to the machine learning model makes all the difference, and that's tying back to like, you know, understanding that data. So yeah, I think that's kind of like a really, you know, kind of the same point, but just a different angle on it.
Yeah, I think it's kind of machine learning is really impressive to us because it can kind of consider many variables at the same time. We then kind of overestimate its ability to make logical leaps, and actually coming at it from an angle is like, how could I make this data easier for me to solve this problem? How could I represent this so it was a simpler space to reason within? Can actually be quite a powerful way of thinking about it from a machine learning perspective as well.
Absolutely.
You can just scale it up to wider things.
And now you cut into one of my points, but like, why don't you do your next point, and then we'll jump back to that one.
Yeah, this is a bit of a niche one, so it doesn't apply to everything, but where you have like human-generated data, it's just super important to understand like, well, who generated it, you know, when, what was the policy, you know, if you're having people tagging things or labeling things, especially if they're doing it for the purposes of training data, are they kind of doing it in sort of duplicate to factor out the kind of human error that you get anyway? So now we've had a few examples, obviously, without going into specifics, where we've been trying to sort of replicate a really arduous human tagging task, and what we found worked really well was getting the same 10,000 observations done by 3 different teams manually, and then taking kind of like the modal averages, like the ground truth. And we found in that case the model was actually better than any single human labeler, and that's because you kind of like the errors cancel out. If you don't have that kind of thing, you just introduce all that sampling bias and labeling bias into your algorithm, and it's actually going to be very hard for that to ever supersede this accuracy achieved by the human labeler, if that's your goal.
That's a really good point. That's what I hadn't actually thought of for this. You know, I think there's two things. Basically, sort of like you start a project and people assume there's no human error, or they have just too much faith in the labels in their data.
Yeah.
And actually, almost always that you know that there's more error than people would imagine there is, and actually sort of correcting for that error. You know, basically doing some relabeling exercises, doing those multi-samples. I mean, it just pays dividends almost every time. So yeah, that's a great one.
And it's typically not until you have to actually do something like data science with that data that it's become a useful exercise, or shall we say valuable, for them to start to worry about that error, because it's only making everyone look bad.
Yeah, it's the sort of thing of it's sort of like, this is how we, basically when we say this is done, it's something like a legally binding thing, and finding out that there's error in it is...
We're rounding 1% to 0.
Yeah, it's kind of an uncomfortable process, but I think the thing is that the people who kind of can get comfortable with the fact that there is error in the data and make that work, they're the ones that basically reap all the benefits. So it's sort of, it's kind of realizing we're fallible, working within those systems, and getting that better. Yeah, 100%. Great point. All right, so now kind of just shifting backtrack all the way to the other one where we're sort of like talking more about sort of like the data and people's understanding of it. My point is, I've titled it Sherlock, not Merlin, and I end up sort of saying this quite a lot. Right?
Yeah, that's nice. I like it. Could be a catchphrase.
Yeah, and I think the thing is here is like, okay, so imagine we're looking at e-commerce shop data, and we've got the past 50 purchases for each customer, okay? Can you predict the name of their first child?
Easy, yeah.
But no, it's not possible. And actually the thing is that there's a whole bunch of people who just seem to think that there's some sort of magic that happens within machine learning, and that maybe it could, And I think, so the way that we need people to think about this is more like, what sort of information would a super genius need to, like Sherlock, to figure out basically like what the name of your first child might be. So, maybe that's like, okay, I'll take your family tree. I will have the names of everybody that you went to school with, everybody who you went to a sports club with, everybody who you dated. I want to have all of your Facebook and Instagram data, who are you looking at, who are you liking, basically sort of maybe like, all of your messages to say like, have you ever sort of like talked about baby names or something like this, historic records of popular baby names throughout history, what TV shows are you watching, maybe the scripts for those shows, so we can like parse them for baby names as well, and you're saying, right, like, I mean, you don't have to know how all this information could be used or exactly how to link it together or any of this sort of stuff. You just have to think sort of like, if I had a super genius and they had infinite amount of time to pore over all of this information to try to figure out that one answer, what information might be useful to them. And if you think like that, then you're probably going to create a really good data set for machine learning to learn from. But if you're expecting magic, you're probably not going to get very far.
I remember like the first year of uni back in about 2006, and learning about neural networks for the first time. I was like, it's like a human brain, it's going to be just like better. And trying to get a neural network like 2 layers, like 5 hidden units or something to like predict the next number in a pseudo-random number generator. It was actually preposterous if you actually understand the maths and how difficult that would actually be. You probably couldn't even do that now very effectively with like a massive model, let alone with a tiny little 2-layered thing. But it's just had that. It's just an appealing black box, isn't it? And especially if you don't fully understand yet what's going on inside it, it's kind of tempting to just bestow upon it kind of magical powers of intuition it doesn't actually have.
Yeah, like I said, I think sort of like one of the biggest ones for us where we kind of end up having to have these conversations that are like a little bit uncomfortable with the client is sort of like often around sort of magical thinking around data. They kind of go, hey, we're so excited about this, let's do this thing, and then it's like, here's my data set. And I mean, I think like like the most ridiculous one I think I saw was like there was 50 different classes to predict. So it's basically sort of like they want us to be able to predict combinations of these 50 different things with like 8 examples, you know, and that's just like it's impossible, you know, like it's just like there isn't even an example of every single combination or close to, or even each individual thing, never mind the combinations of them. So how is it supposed to have the sort of layer of data to learn from to do that? But I mean, you know, I suppose the thing is that, you know, I mean, to us that's like, I mean, how could someone not do that? But then, you know, I suppose you come along with transformer models now, and sometimes, like, if it's something that's within, you know, possibility, you do come along with like 4 examples, and suddenly it does magic. So I can see how other people might have the impression, and actually, you know, in some cases that's not always the worst thing. But I think the thing is, if you're thinking about like modeling on your data or on a business domain data where there's no sort of prior billion examples to learn from, then you're going to need to have a lot of examples, not be able to have the magical thinking about data, essentially.
As a rule of thumb, having more examples in classes tends to work. Yeah, we do. Transformers have a lot to answer for like reviving magical thinking, maybe. But getting more people excited than they are at the same time, so, you know.
And they do some magical things.
They are pretty magic. They are actually magic, to be fair. Alright, is it my go?
That's your go.
Can you get at the data? Can you actually get it? Actually, can you get it? Because, you know, often you might think you can get it, but it might actually live in a database, you know, that's quite old and creaky and not replicated and supporting production system, and the query you need to run to get the sample you need is something that might actually jeopardize something in production, and actually, you know, you wouldn't necessarily know that. You'd had a sample of the data, you've seen it, and you have to go quite a long way down the process before you realise that's the situation. So it's all about having those conversations up front and really getting the people to understand the data stakeholders in the room as quickly as possible. We touched on this last week. There's also the case where you've got multiple kind of disparate silos. So you might kind of technically have that information. So a bank will have, you know, things like your credit score, and it will have maybe things like the things you complain about from the contact centre, let's say, and, you know, maybe what you sort of preferences were on the website. And I'd be very surprised if many banks have a single view of all of those things nicely joined together, and it's actually often nigh on impossible to get those things just sort of joined. There might not be a way to join them, for starters. They live in the domain of multiple stakeholders who aren't necessarily that bothered about just helping you do, you know, try something that typically with data science you haven't proven it out yet, because that's why you're doing it. So, you know, there can be a lot of friction in just, you know, yes, we've got the data, but no, we don't have the data in a way that we can actually use it. Essentially, even if you've got the data in a place where you can get it, do you have the right way of joining it? And sometimes some of these systems weren't designed to be able to be joined up. Like it's like done on something that's kind of works for the purposes of the business, like first name, last name, or something like that. Which is like perfectly fine if you're only processing like 10 sales a month, or, you know, 10 sales a day even, then you just need to reconcile those, and for every so often it doesn't quite work, you just manually tweak it. But to actually create a consistent join across like a large period of time, it means you get a lot, you know, a significant number of misjoined things and all sorts of nightmarish scenarios. So just, you know, had that database been designed with a proper kind of foreign key and whatever, it'd be fine, and it just wasn't because they weren't thinking about doing data science when they set it up. So, you know, you can have the data but not have it in a way that's of any use.
Yeah, no, that's a really good point. I think sort of, you know, like a lot of the sort of, you know, our last discussion, which was around the road mapping, is really trying to, you know, work with people to identify up front these sorts of issues, so we can sort of like not run into them sort of midway through a project. But obviously sometimes, you know, you get started on projects for, you know, whatever reason, and, you know, these sorts of things happen, and, you know, try to work around them. I think the other thing is also, it's kind of probably, you know, it's kind of correlated, but you sort of like when people are doing data lakes and when people are doing that sort of thing, a lot of the time what we see is that people sort of say, oh, I'm going to move my data to the cloud, and I'm going to have this great resource that everybody's going to be able to use, and it's going to be great. And then they just think, oh, I'm just going to, just aggregate these records, and it'll save space, and I'll have all this stuff. And then the thing is, like, machine learning needs those records, like, in a lot of detail, And so, I mean, there is a big move now towards sort of like saving raw data and then having the sort of transformation layer afterwards, which, we totally buy into that. So I think the thing is, like, one of the recommendations would be is, like, if you're trying to get that data layer in place, if you're trying to make it that you're going to have that shared accessible data, do try to make sure that you're saving things in as raw a form as possible, because the more processing you do before you save, the more likely you're just to destroy information, which would be incredibly useful for machine learning. And I also think it's also useful for people to kind of do that road mapping exercise to get that view on the data, so that they kind of go, oh, it's probably useful for me to store this and this at the same time, because often that's really easy to do when they're sort of creating those stores rather than later. And I mean, that's also like, at the same time, like when you're making these data requests, often you kind of, in these sort of fraught situations, you kind of have to make a big play to go get that data, and you really want to make sure that you've got, like, that you have a good view on what the data you're going to get is, what it looks like, and that you'll be able to sort of like reconstruct that into solve your problem, essentially.
Yeah, definitely. Now, there's been a number of cases, I think, where we've had like the data, we thought we've had the data, and it's just like beyond a certain point it's been aggregated into effectively useless summary statistics that then you've got 10 for 1,000 for the number of observations you would have had to project forward with.
And what you're saying there actually kind of ties really nicely into my next point, which is beware of self-entered data. So one of the ones we had was we were working with this sports team, and they thought they had this awesome data set. So they were like, oh, you're going to love it. We've got all these demographics. It's, you're going to be able to do the best data science out of this. And then we get a data set and we look at it, we're kind of getting, okay, like a couple of these are nulled out, but there's still quite a lot here. And then you kind of like, then you're actually looking at the value counts of these things. You're kind of like, hang on, there's a huge amount of default values here. And then you actually look at all these sort of demographic fields, which were like optional on forms. So it's like, hey, fill this out and then tell us all the stuff about you, or just click done. Yeah. And people just click done. Yeah. And so, it turns out that only like 6% of the data actually had some of the demographics filled out. And even then it's like not all of the demographics filled out. So I think the thing is like, so yeah, there's a challenge here. Is basically like when you're looking at your data set, make sure that you're really also looking for those, default values, those common things that can show you that like you've got very little signal in there. But conversely, it's probably not worth your while trying to force people to fill those in, because otherwise you'll just end up with a whole load of people who are from Narnia, religion Jedi with the surname Vader or something like that. So it's kind of like, if you try to make people do something they don't want to do, they'll just give you really horrible data, which will be even harder to unpick. Yeah. That you've got rubbish data in there.
Yeah, basically. WASM.
WASM. Yeah.
So I've got my number one, and it's a pretty obvious one.
Ooh.
And it's multifaceted. But do you have enough data? And that's with respect to a bunch of things. I think you touched on some of them actually. First of all, how noisy is that data? And by noisy, I mean, what's the kind of, how many observations do you need to see to kind of let the noise cancel itself out and to actually get it sort of, the thing you're trying to predict appear out of the murk. So an example of noisy data would be sensor data from an engine. So if you've got, a fleet of motor vehicles, and you're trying to predict a reasonably rare thing to happen to the engine, no 10 engines are going to be quite the same because of the manufacturing process. There's like tolerances and things like pressure and vibration sensors are you're just going to need a bunch to just normalize out all of that. Conversely, something like if we're talking about document classification, so we're just trying to find the right type of document, you might need very small numbers of examples there, just because these documents have got all of these words, these documents don't. There's quite a lot of signal for a very small amount of noise, and it's a lot easier. So on one example, you need far fewer observations than the other. And then kind of leading into that, sort of the kind of problem type, right? So if you're trying to solve, like I think we'll agree binary is the simplest, and then something like multi-label classification or maybe regression is the hardest, and as a reasonable function of observations per class or per target, needed there. I think with regression is probably, well, how complicated is the output distribution? Is it like a double-headed whatever? You're going to need more examples, right? So it should be possible to kind of know roughly, as a rule of thumb, ahead of time, if you've got, like you said, 50 multi-label classes and you've got 8 examples, probably not going to work frightfully well. And then you've got to, like, how complex is the decision you're trying to make, right? So that's like, are we trying to predict a second-order chaotic system like the stock market, right? Which is probably the hardest thing you can predict. A system where predictions themselves are being made which affect the system in a kind of recursive loop. And then, on the other side, you've got things that are like I said, very simple, where you've got some very clear markers. So, if you think about the task if a human was trying to do it, how hard is it? How many different kinds of examples would you need to see to be able to confidently make that decision? Or how long would you need to study, if you like? How long would Sherlock need to pore over his notes? And that's directly correlated to how many observations you have, basically. Another factor is just how many features are going to be relevant. And that's proportion. All of these things are, as you might have noticed, quite correlated, but they're sort of different ways of looking at it. So if you've got something, let's say like image data, or maybe like we've got, with some banking stuff, where we've got like 1,500 different views on a person's rolling transactional history, they're all correlated, but they're all reasonably likely to be important to some extent. But let's say, going back to our car example, if we've got like diagnostic trouble codes that relate to very specific things, and we're just trying to predict a fault in the starter motor, and only 4 of them relate to the starter motor, you could broadly ignore the 9,000 other ones that don't, for the light over here or something like that, in a lot of cases. So, if you can chop away a whole load of those features, you could use less observations. So if you can work out, maybe we were only interested in predicting the X, Y, and Z, we could actually get rid of these, then you could get away with less observations than you normally would. So it's not just a simple function of columns and rows, it's like how many important columns and how complex are the things we're trying to predict with the rows.
Yeah, no, I think that's a really good point. I think so I think you made 2 points in there, which I think maybe can be sort of like said in a simple way. I know obviously people might appreciate the sort of complex way you've put it, but I think sort of the idea that, how many examples would a human need to solve the same problem? And I think that's like a really good one for people to be able to sort of rule out some of those really, silly data sets that we see. I think the other point there, though, is that sort of like, in terms of numbers of examples, computers learn, or machine learning learns slow compared to people. So, like, I don't know whether it would be, a person might pick it up with 3 examples and a computer might need 30, or if a person would need 30, then the computer needs 300. I don't know if it's as simple as a 10x multiplier or something, but there's some sort of fudge factor there for, machine learning will likely learn it slower. So when you're thinking about numbers of examples, you're probably looking at sort of more examples for the computer than you are for the person, right?
Yeah, probably.
And then I forgot the last one, so let's move on. All right, cool. But yeah, no, I really like that. And I think the thing is like, sorry, just going back to that one, I think that, the challenge there, I suppose, if you were trying to sum up the takeaways for someone, so obviously, I mean, like the thing is, there are a lot of things going on in the data, but if you're trying to sort of say, hey, I'm looking at the data before I have got my hands on it to a certain extent. And obviously, like, once you get your hands on it and you can sort of say, well, actually, like 12 of these 300 columns are the ones that I really need, so I'll just focus in on them, and then actually I don't need as many, examples. But what would you say to someone, sort of like, what should they be, how should they be thinking about it? Is it as simple as the rules of thumbs that I talked about before, or have you got sort of like other advice for people?
Yeah, well, I mean, it's incredibly hard to just, like, I think the rules of thumbs are a good starting point, or trying to pretend you're the computer probably is a good place to start. But then it's like, it is just a function of things like what you're trying to solve, and, how many things are likely to be important and how many columns are there, and all of that kind of stuff. So yes, it's obviously an intuitive thing after a certain point, and you can kind of grasp it. Then obviously there's the rule of thumb that more data is better is definitely true, but I think the rule of thumb about the classes is probably an important one as well. So like if you've got just one binary class, then well, how often does that thing happen? Does it happen more than 50 times? You're probably good. You could do something. That's a good starting point. And to bear in mind that most problems don't need to be as complicated as often they're made out to be. It's amazing how many problems can still have some sort of business impact as a binary problem. Okay, even like something like product recommendation. Are they going to buy a product at all? Like, it's still maybe useful.
And I think one that we often see is basically it's like how much are they going to spend? And actually it's really like, are they going to spend more than this? Because that's what we really care about. And it's actually if you convert the regression, because often the challenge with that one would be sort of like if you're looking at a regression, it's actually like the majority of the examples are sort of like at the mean, and people really want to predict the high value stuff. So then the thing is the model gets really good at predicting median values and actually not so good at the high value stuff because it's looking at sort of like mean absolute error or something like that. Mm-hmm. And so, but actually if you just have a cutoff, which is like how well can I predict this cutoff between high value and low value, then suddenly different features are going to be important. It's looking at different things. It's really sort of trying, it's basically the difference in the things in the sort of middle belt where almost everything is are just less important for that. So you'll just get a much better model. So yeah, that's a really good point as well. Cool, so my last point is the rules are probably less strict than you think. And so just, this needs a little bit of backstory to kind of get into a little bit, but it sort of follows in from that thing of, nobody ever got fired for buying IBM. That sort of old adage and all this sort of stuff. And really what that talks to is the asymmetric reward versus in enterprise. So basically sort of like if you preside over one pretty big fuck up, that can be the end of your job. Whereas like you can preside over like a big success or just a couple of minor successes, and as long as you're not fucking up, you're probably going to be able to climb that ladder pretty steadily. You're probably having like a big win probably doesn't change your trajectory all that much because you have to wait for positions to open up above you and all this sort of stuff. So really there's just this asymmetric risk to something going wrong. And then basically often what you have is in a large enterprise you're going to have like a data team which is separate to the team maybe that has to work with the data, or you've got a data person whose kind of responsibility is the data. And so they sort of see it as their thing of like, well, I'm going to create the strictest sort of set of requirements I can think of on the data because I just don't want anything to happen with the data because that's going to reflect badly on me and that can cause like a lot of, that can stall things that could otherwise, work okay. So I think sort of the first rule that sort of people tend to be like, maybe like over-egg a little bit, is that they sort of say, oh, well, we've only got this data for this one purpose, so we can't build a model to try out that other use case to see if that would be good because they didn't give us permission to do that. So if we were to do that, what we need to do is we need to go and ask everybody permission, and we think it might be high value, but we don't know, so we can't go and put all that effort out to ask everybody for permission to use their data to try this new thing, which might actually provide a better service for them and do all this sort of stuff. Until we ask them. So you kind of have this chicken and egg scenario of we can't do it until we get the data, but we can't give you the data without the permission, so it's not going to go anywhere. Whereas actually, like the people who sort of created the Data Protection Act were actually considered this already, and they put in provisions for research. Now I'm going to look at the rules for the caveats on this. So the restrictions are that the data cannot be used to make decisions about an individual. So if you're using it for research purposes, even it can be used for commercial research purposes, but you just can't then take this research and then make a decision that affects the person. You have to be like, oh crap, I shouldn't have lent to that person, so now I'm going to rescind the loan offer, or I'm going to rescind that job offer, or I'm going to change how their credit limit, or all the whatever it is that you might do. You can't then just take the research and then take that back into your business and affect that individual in a different way. The data cannot be used in any way that could cause distress or harm. So you can't basically sort of suddenly say oh, I'm going to sort of, psychoanalyze my my customers and really freak them out by, I mean, there's that sort of a powerful example of Target where they suddenly sort of like ended up sending this sort of teenage girl stuff about her pregnancy before she realized that she was pregnant, and then the dad was like, what's going on? Turns out she was actually pregnant. But, so you're going to be careful about how you're doing the data. You wouldn't do it in any way that would cause distress or harm. And actually, like, if you're not taking an action back, if you're going to just test against historical data rather than actually do anything with this, because really, to get the use case going, really all you need to do is you need to prove the value on historical data. You don't need to take any actions that affects anybody or risk anything going back into the system. Once you prove that value, then you might sort of unlock the impetus to go, oh wow, this really is worth sending out to everybody to get everybody to sign off on can we use their data for this thing, in the real life system. The other one is that the research is not incompatible with the purpose for which it was collected. So basically, you can't sort of collect everybody's data to be like, we're going to match you with the best doctor, just send us your medical records and we're going to hook you up with the best doctor, and then you basically kind of go, hey, we just did a whole bunch of research that we can now sell to an insurance company, which is going to block half our customers from being able to get insured. That would be completely incompatible with the purposes from which you obtain the data, so that would be restricted as well. And then basically also any resulting statistics or outputs from the data cannot identify the individual. So but I mean, that's also okay. So like all these restrictions are pretty much fine. If you want to back test a model, to sort of figure something out, you're not really going to violate in almost all these cases any of these restrictions. In which case you're actually free to do that back testing, prove out the value, then scrap everything before you go to do the real model. Basically, just keep the techniques and all this stuff and scrap all the data. Get everything signed off, get everything done, and then you can do that in real life. And then you can unlock that chicken and the egg, which I think it makes sense that they would make a provision for this. It's just that often in organizations they sort of go no, so it's sort of. Trying to work with people to kind of get that understood better and unlock that. And then you might find that something that you thought wasn't good data, that you couldn't get access to it, you actually can get access to it and you can do something good with it. I think the other rule that I hear about that I think people kind of get a bit wrong as well is that sort of like, the Information Commissioner's Office Code of Practice is like really clear on the fact that basically while zero re-identification risk from PII is desired, it is in no way what is required. It's like re-identification needs to be a remote risk, but that's very different from being like zero acceptable risk, So I think the thing is like you often get people to kind of go, oh, we're just going to go with the zero option. And actually, like if you're going to try to do meaningful things in machine learning, like we just talked about, a lot of it comes from re-engineering the data. So if you basically kind of take the zero re-identification risk, you kind of go, we're going to tokenize absolutely everything, we're going to hash absolutely everything, then you're not giving the data scientists a chance to reimagine how to work with that data, to understand the data, which was like one of your big points about what to do. So like the chances of them actually getting a good model out at the end are like super small, unless it just happens to fall out of the box. It's just not going to happen. So given the fact that we want to keep the chance of re-identification a remote risk, but we also basically want to like keep the data semantically meaningful, basically, like and understandable and something that we can work with, like what are our recommendations for how you do that, right? And I think the first one is basically, if it's not PII, don't obscure it, like if it's basically like, what car did someone buy? Well, loads of people buy the same cars, there's nothing particularly identifiable in that, what's someone's favorite song? Not particularly identifiable, so like, those sorts of things don't need to be obscured at all. Then the other thing is that basically, if you do have a field which is PII, then yes, absolutely, like, if it's pure PII, tokenize it, hash it, and actually, unless it's particularly useful to the model. Like, I mean, for most models, knowing someone's name doesn't make any difference. Like it's
If
not.
anything, it's like problematic in terms of injecting bias through like surnames and whatever.
Yeah, so it's basically like in most cases you're actually like, okay, like if it's just pure PII, remove it from the model from whatever you're trying to do. But then you might have something like a postcode, and with a postcode, then it might be sort of like going, right, well we could sort of have the postcode to a certain number of significance. So there's enough people in the population, like we've removed enough digits from the end of the postcode that it's sort of still meaningful, but it's now there's a population of like 1 million people that it is of, rather than sort of being sort of like down to 1 in 100 houses or something like that, or potentially even one house in some cases. But the other thing that you can do with that sort of thing is sort of swap in something. So a lot of what we end up doing is kind of like go, right, well let's actually like get rid of the postcode, but what we will do is we'll supplement in things like the census data or all these things. So it's basically like what we're really interested in, like how educated are people in the area, what's the average house price in the area, what's the average different rate of crime, or and you basically put these different factors in, and then basically now it's completely non-identifiable, but you have all of the pertinent information that the model was proxying from that data available. The other thing then is basically some fields are like email, right? And then you've got emails, and actually emails can have like loads of great information in them for doing loads of really meaningful tasks with machine learning, loads of automation, loads of things that you can help people with. But obviously they can also contain a lot of personal information. So I think the thing is basically it's like when you're dealing with these fields, these are the sort of like really sort of like problematic ones, but there is still ways that we can work with them so that they can still keep that remote risk of re-identification, right? So we can basically say, right, well what if we use a whitelist for dictionary, okay? So that just means that sort of like we're just going to say all the normal words, so it's like, run, bank, walk, and we know that they are not personally identifiable. So we're using a whitelist of words that we know aren't personally identifiable. And then if you're using a whitelist of those sorts of words, then it's going to be very hard for something to sneak through that could identify someone. On top of that, you use a blacklist of names. So you take like the biggest name database you can find, and you use it to blacklist all names in the text. So then basically you make sure you're not actually putting any names back into the text. And then what you can do is you can basically say, right, well actually let's also use named entity recognition. So instead of making it sort of like, instead of just like having bits missing, you can kind of say, oh, like, so where it would say, hi John, it now says, hi person one, and then basically sort of like, it's like, and then it might be like, can you send this over to person 2, and I'll meet you for coffee at place 3, and at time 2. So you end up with all of these things which could be used to identify anything as sort of like replaced by things which are location, person, but the rest of the text still reads because you've sort of whitelisted all of that. And I think sort of like, even though that's sort of a much more complex technique to sort of build together and work, it means that you still have that really remote risk of re-identification, and you have something that's meaningful to a data scientist that they can still work with. Now, just to say basically, there's a lot of technique in there and you might not want to implement it yourself. We'll link like a thing to our docs in the description. We've got a free package that you can install and use the anonymization if you want to. But like that's like an approach that we take. If you've got other takes on it, we'd love to hear yours. We're really trying to like do that in line with the Data Protection Act and the Information Commissioner's office. Cool. So, did you have anything you want to add on that?
That's a lot. I'm just still fantasizing about the companies building models to freak their own customers out, to be honest. I predicted your biggest fears.
Let's recap our top 5 takeaways. Now we've kind of like done them all in detail. So why don't you go first and sort of like talk through, just kind of give us the bullet list of what they are.
I think if I was to change my list, I probably think a few of the things you said supersede it. Like I think probably understanding what your target means probably would come a lot higher. Maybe put that, I'd say having enough data is number 1. Knowing what your target actually means would probably come number 2. 3 would be actually understanding what's going on, like what do these features mean, really getting to grips with your data. I think the other stuff broadly would be the same, like, can we keep access to it, can we actually get at the data.
Cool.
Yeah, how about you?
Well, I'm not going to attempt to redo my list mentally on the fly, so I'm just going to...
Just ask me that.
Well, I was just like, I just meant like repeat your list, like kind of like we've kind of gone through a lot since then.
Right, okay.
Yeah, sorry. As you can tell, this is not very rehearsed. Anyway, so my top 5 takeaways were the rule of thumb for targets. I think that we use that a lot. I think sort of a lot of what you elaborated on is really useful, but I think the thing is like we just keep on coming back to those same simple, like, can we do it? Should we even use this data set or not? Those are the kind of rules we touch on. The Sherlock, not Merlin, I think that's also one, just not, no magical thinking.
Yeah.
And then, representation matters. So it's equally how you represent the data versus the algorithm that you're going to pick to solve the problem with the hyperparameters. And then beware of self-entered data. So that was just, one of those other ones. And then basically the rules are probably not as strict as you think. So like it's kind of like that thing that there are actually options within here that sort of the sort of like what you hear around and what the actual rules are a little different on some cases, and that can be the difference between being able to actually really extract value from data and not. So hopefully, I mean there seems to be a bit of overlap in a bunch of them. Like
I think we came at it from slightly different angles, but there's broad kind of intersect there.
Yeah. Okay, so basically, I mean, I think we kind of touched on this before, but basically, what's any particular sort of like ridiculous data set that you've ever seen?
I think we touched on it, didn't we? Like 8 observations in 50 classes springs to mind.
Yeah.
Or things where there's the target isn't in there. That also is quite tricky. I've done that a number of times as well.
Yeah, for sure. What's your view on synthetic data?
I think it's largely pointless because, there's a few. I'll just caveat that by saying I can think of a few examples where it isn't, and that's like something with like image processing. When we got images, and you want to create extra examples where you've like permutated the image. Might be an analogous one in NLP where you can, add if you're doing something character level, maybe add a bit of noise, add some extra characters. Or maybe even on word levels, just like permutate, swap some words around, put some synonyms in, just to kind of make us, it's not going to have a huge difference, but it'll make your model hopefully more robust to noise, as long as the noise you add is reasonably realistic with respect to the real data in the real world. But like you're not going to make your model any better by generating synthetic data, really, because if you know how to generate realistic data, you don't need to build a model because there's a set of rules you could just run. It's like kind of axiomatic, isn't it?
I think the thing is that sort of there's a big sort of push on sort of like people going, oh, I don't have to give over my real data, I can give over the synthetic data, and then I'm sort of like covered from a lot of those potential risks and all this sort of stuff.
I guess if you mean by synthetic data, like some projection of real data such that you're capturing a distribution and things, then that's slightly different. But again, it's not as good as having the real data with some proper anonymization.
So some people do use it as a proxy for, they think, oh, I've got the synthetic data, there's these people who say they can create these really high fidelity data sets, and then I don't need to give out my real data, and I'm going to be able to do machine learning, it's the best of all worlds, this will be great. And I agree with you a lot on the fact that sort of like, it's super risky to do this, and actually like, I think that the key challenge is like, it's sort of like Chinese whispers. It's a copy. Now it might actually be roughly the same thing, in which case it might actually produce a reasonably good copy and you're good. The only problem is that it might also be utter bollocks, which happens to look right just enough of the time.
Yeah.
And so you could, and I mean, if they're really focused on sort of like, recreating things that look sensible, but they're missing their sort of adversarial function that allows them to generate this data is not as complex as the actual surface of the problem that you're solving. Then you're just running like a massive risk here. So I think that sort of using the synthetic data, en masse is probably like not a good idea. I also agree with you basically that the idea about like where we do see it used well is when it's used to augment a data set. So, like your example about images is a great one where you can augment almost every image because we kind of know how images work, and you're like, oh, I'll just rotate it, I'll just do these things. But to a machine learning model, they're different examples, they're really meaningful, and this sort of thing. Whereas, there's also other examples, like if you're sort of saying, people are doing credit lending. It's like you don't have examples of people that you didn't lend to who defaulted.
Yeah.
So you have to sort of create a population of those things, and that's actually okay because you're sort of saying, right, well, I'm going to model these people. I understand what they should be, and I can. It's better than nothing in that case.
Yeah.
I think another example, like if you're watching the Tesla AI Day, they were actually using it to sort of like model like a family walking down the middle of the highway. Now it's not something that probably they've ever come across, but just in case you end up with that, you want to train for these like crazy conditions that we can imagine that we may not expect to see in a data set. So you can basically sort of augment your data set with like, well, I really don't want it to do this, and I really don't want, like, this would be super terrible, so let's put in negative examples around this, and this would be super terrible, so let's put in negative examples around this, and you're like, just build that out into the data set. And another thing that they were showing was actually like where there is a failure, by having this sort of simulation, they're able to say, oh, okay, well, like let's basically have that same failure. We'll create the corrected action, and then we'll do that corrected action on a different street in a similar scenario at nighttime, at daytime. Where does foliage? Where does this sort of thing? And so you're creating like you're able to sort of create many examples of one edge case that failed, create lots of examples of what to do right, and sort of help to sort of augment and fix your data. So I think sort of synthetic data as a way to fix or augment a data set is really good. And actually, like we're totally supportive of that. Where we're not supportive of it is basically as a wholesale replacement to a data set, I think.
Yeah, I think it depends. I've thought of a few other examples where it isn't terrible, which would be like something like Smote, where you're just generating extra examples, and sometimes like some machine learning models might be really good for solving this problem, but that's terrible when you have unbalanced data. Like neural networks really don't like it. So you might be wanting to use a neural network, but we'd never recommend, we'd always recommend using an algorithm that works well on unbalanced data sets, like gradient boosting. If you hyperparameter tune that properly, will do really well. But you might want to use a neural network for whatever other reasons. Smoke gives you a way of balancing the classes so that you can use it. And then the other scenario is, again, a bit of an edge case, but where you're actually able to have like a simulation of what you're trying to model, and it's a perfect simulation or it's close to a perfect simulation. So if you're creating some sort of machine learning for like, maybe CAD or design or like a computer game or something like that, where you can actually create scenarios to create training data because you're trying, just want to give more examples to the model. And I guess that's kind of what Tesla are doing. Like, they don't have the opportunity to actually enact these things in the real world, so they're just building a super realistic simulator because that's better than nothing. But yeah, if you, for whatever reason, machine learning models running in a sort of simulated world, so maybe like AlphaGo, that's a good example. It's just you're trying to model a game, so you can just create examples willy-nilly.
Yeah. I mean, and that's great. And if you've got like a closed system where you can create perfect examples, then because I think one of the challenges is actually, transformer models are probably almost better at everything because they can model much more complex surfaces. The challenge is generally you don't have the training data to train the model like that, or reinforcement learning. Again, you wouldn't have the training data to train something like that. But if you've got like a billion examples because you can do it in a simulator, then you can get up there to train those sorts of networks, where for a lot of real world sort of business problems, you just don't have that sort of data. So if you have that sort of thing that you can perfectly simulate, then you can create that sort of data as well. So one of the popular use cases we see is around AI automation. So what would you say a good data set for AI automation looks like? What would be your sort of key points around that one?
Well, it tends to be a human-labeled data set in that case, or you've got a process that's being carried out, and you're trying to basically you're trying to find sufficient examples such that you can get to a level of accuracy on a subset of that data where you're kind of doing a useful job. It would be like a human-in-the-loop implementation. So basically, you need to, obviously consider the things we talked about, which is like, how is the process happening at the moment? What's the error rate of that process? If people are actually being asked to create training data, making sure you have things done in duplicate or triplicate to, to kind of cancel out the errors that will come with that. Yeah, and just I guess knowing who's doing it. So if you might have specific people interpreting the policy and what they're doing slightly differently, knowing who did what when is a way to sort of account for that bias and hopefully remove that.
Yeah, no, I think those are great points. I just like, I think adding to that, I think sort of like when you're starting to think about your data set for automation, it's really about sort of thinking about, and they are a great use case for AI, but it's about thinking sort of like, do I have digital data coming in? Do I have digital data coming out? So like what processes have that sort of data going on? And also a key factor here is that like with the digital data coming in, that they're not then going off and using the internet to do a whole bunch of research, and they're not sort of, then handpicking a bunch of sources, but but that they're actually sort of making the decision based on the data that's coming in. So you've kind of got full sight in the system of all the data needed to make the decision for the outputs. And then I think the other thing is like for the outputs, it's either trying to like predict like one or a small number of things. So like an example here, and I'm just going to get some others up, but basically, like should I give this person a loan? Maybe it's like yes, no, maybe. That's a small, you're going to look at all of their transaction history, you're going to look at like, their credit history, all these different things, take all these decisions into account. But then the output decision is quite simple, and that's generally like a good sign that it's sort of like, going to be easier to automate. Because obviously, almost like every single output you're adding is another model you need to add to the system to kind of, and we create some more complex solution to kind of get there. Another example might be sort of like, how much should we insure them for their holiday, or for this business, venture they're going on. And it might be like, oh, the output of the model is like 300,000. So, there it's like, it's a number, it's a regression, so, but it's still sort of like a single answer. Another one could be sort of like, sort of like, what products should we recommend to them? And so it could be sort of saying, mortgage, cars, credit card, and there's 3 different things we want to recommend to them, but that's more of your like multi-label, given the sort of things that we have, what would we try to predict? So I think sort of like, it's like trying to find a digital process where all of the sort of the decision criteria are known and are part of the process. I mean, one that we often see as well is basically sort of like there's sort of like a whole bunch of people in a business who are like, oh, how can we give a quote? How can we give a quote for this thing? And they've got some guys who've been in the business for ages who look at all the different factors and kind of give a quote. And they'd love for other people to be able to give a quote, but it's sort of just those guys. Or you've got something about sort of like, how much do we think this product is going to sell given all these factors about a product? And it's like, oh, well, like, you can use machine learning to try to sort of replace this sort of, key man system or support it, or not necessarily to replace it, but sort of like to support it, augment it, give you a bit of sort of like, more standardization, because machine learning will sort of take all the different experts and kind of group them together and kind of get a more consistent, way of you working. But I think sort of those would be the 3 things for me would be sort of like, in terms of like that sort of how to get started. And I think sort of like then what you're talking about in terms of, making sure that, we've got triplicate in the checking of the answers in the system and all this. So I think that sort of applies probably like, after those sort of more basic. I think I was thinking from a more basic perspective. You kind of done this sort of like, kind of after that stage. All right, cool. So, yeah, have you got anything else you wanted to add on the data topic?
No.
So a lot of what we covered here were sort of rules of thumb for how to think about data and how to sort of try to understand if a data set will be predictable before it is. And actually, Alex covered off a lot of like why, even with those simple rules, it's really hard to predict up front. And so what we have done is we actually built a tool which is like Dataprep, which we'll link in the description, which does help you, like once you've got your hands on the data, you can really quickly, easily see if it is predictable, how predictable things are, and a couple of key insights about data. We really built it because we were seeing these data challenges and we're like kind of going, oh crap, like it would be so useful if we just had something like this that could just do this analysis and let us figure out if it's go, no go for a project. So we generally try to get a data set before a project starts, run it through this tool, and then basically try to see, like if basically understand where we're at before we start a project and deal with resourcing and stuff. So, okay, just a quick look at this tool. Basically, once you upload your data set, you can just basically sort of like see a data overview. You then have this sort of data completeness, so we can see here like name removed for PII purposes probably. Then we've basically got sort of like marital status. This is one of those sort of columns where there's a not specified, so there's a default value. We just want to get rid of that. Then if we're looking at sort of like column insights, I'm just going to collapse this a second, but down here we can see it's telling us like there's a leaky variable in our system, so anything that it's telling us about how predictable it is, we should probably ignore it because it's going to be like overly optimistic. So we can just sort of like click on to basically click that to remove a column. Then it's also telling us that there are 2 columns which have like little bearing and removed, and this is actually really useful when you've got a really large data set. Now this data set isn't large, but when you've got a really large data set, it's basically kind of like that thing. It's like we might have a data set which is 3,000 variable wide, and then we might think, well, it's only 1,000 rows long, and that's not a very good data set because you want your data set to be at least sort of like generally like 10 times longer than it is wide. But if there's only signal in sort of 10 of those columns, and we can remove the others, then maybe it's actually okay, and there might be strong signal in there. So this sort of like helps us understand that sort of stuff really quickly, and then we can dive into the predictive columns here. And this is sort of supposed to be like, this is a mobile phone company's like churn data. So obviously sort of is like, why might they have left? And so bad service if the average signal strength is low. So we can see there's a high correlation of people with bad signal strength and then leaving, which is unsurprising. And actually sort of when we look at monthly payment, people who left for a better offer, generally they're the ones who were paying more. So you can kind of just like really quickly start to get insights into your data, and then also sort of like around your target variable, like how predictive are these different things. And again here we can see that sort of like obviously there's leaking variables, so we should remove that, but we can see that 2 of these things are really not predictive, and it's advising us to group them into another. So this is one where there's 3 different ways that someone churned, but really the question we're trying to answer is are they likely to churn, not necessarily why they churned. And if we group those 3 things, do this, then we'll probably find that we get a good answer. So I mean, like, this is a useful tool you might find useful. Hopefully you found this session pretty good. If you did, please like and subscribe and do all that sort of stuff. And yeah, we'd love to hear from you. If you want to check out like the platform or talk to us, or fill out the form on our website, Kortical.com. Hope that was good.
Cheers.
Last point.